video, I'm going to go through the notes on basic probability and independent and dependent events. And we're going to let this question, how likely is it that I will win the lottery, guide us. And the answer is not very. So basically, all probabilities are calculated with this formula that I've written out in words. We've got the number of things we want, or outcomes we want, divided by the total number of possible outcomes, and that's going to give us the probability. So let's take the lottery, for example. A simple lottery involves selecting a number between 0 and 1,000. The winner gets $100. Each ticket costs $1. If you buy 20 tickets, how likely are you to win the lottery? Well, let's assume all 20 tickets are different. There are 1,000 ways we can, or in between 0 and 1,000. I suppose if we include 0 and 1,000, there are 1,001 ways that we could draw a number there. 1,001 numbers we could choose. And if we buy 20 tickets, then we are covering 20 of those possibilities. So how likely is it that we will win this lottery? We do 20 divided by 1,001. And that is not very likely. Almost 0.02% chance. And if we had done a little bit simpler, I think it would have been exactly 0.02. So not very likely that we're going to win that lottery. But the point is 0.1998. The point is, we had the number of ways we could have won divided by the total number of ways the lottery could have come out. Of course, most lotteries are much more complex. In the Texas lottery, you pick 6 numbers between 1 and 54, inclusive. That means 1 and 54 are included. Each number may only be used once, and the order of the numbers does not influence whether you win or lose. So this should be queuing you up to the last lesson that we did. If you match all 6 numbers, you win the jackpot. How likely are you to win the jackpot if you buy 10 tickets? So first ask yourself, how many different ways can you select 6 numbers from a group of 54? And this is a combination because we don't care about order and we can only choose each number once. So our denominator, all the possible ways we could this lottery could come out, is 54 choose 6. And how likely are we to win if we bought 10 tickets? So we're going to do 10 divided by 54 choose 6, and let's go ahead and put that out into a fraction here. If we do 54 choose 6, that is quite a large number. 258 27165, 258 27165. And then to find the percentage, or the decimal value, we would do 10 divided by this guy. So that's how likely we are to win that lottery, which is, let's say it's about, let's go ahead and convert that to a percentage by dividing by 100, or by multiplying 100, 0.0000387%. So not at all likely to win the Texas lottery, even if you bought 10 tickets. The complementary probability is instructive here. So what we do for complementaries is we subtract our odds of winning from 1. And if our odds of winning was this tiny percentage, let's see. In fact, I think I should be subtracting not just the percentage, but the actual decimal value. So I'm going to put 2 extra zeros in here. And if this was my odds of winning the lottery, then my odds of losing the lottery are 1 minus that value. So way over 99% chance of losing the lottery. 0.99999. chance of losing. Okay, so complementary probability and basic probability go hand in hand here. Okay, next question. How does driving your car influence the odds that you are allergic to dairy? Hint, it doesn't. So drawing numbers for a lottery is a classic example of dependent events. Because the lottery numbers are removed from the game after they are drawn, that is, the odds of one of your numbers being picked are slightly higher after each number is called. So considering the previous example more closely, suppose you are the lucky winner and all of your numbers are called. What were the odds of one of your numbers being drawn on the first pull, the second, the third, etc.? Okay. So you chose 6 numbers. So for one of your numbers being drawn, the likelihood is 6 out of 54. Okay, yes. Suppose you are the lucky winner and all of your numbers are called. So the odds are 6 out of 54 on the first draw, and then on the second draw, you now only have 5 numbers of yours that could be drawn out of 53. And then on the third draw, there are 4 of your numbers left out of the 52 left inside of the lottery. And then on the fourth draw, there are 3 out of 51, then 2 out of 50, and then 1 out of 49. Now this is if you win the jackpot. And then you can describe this pattern. Obviously the numerator is decreasing by 1, the denominator is decreasing by 1. But the point is, your odds are changing from one draw of the lottery to the next. Let's consider a different kind of lottery based on independent events. In this lottery, the outcome of one event will not influence that of the next. Example, 6 dice are rolled. You choose one number for each dice. If you guess all 6 dice values correctly, you win the jackpot. What are the odds of guessing the correct numbers for each dice? So you only get to guess one number per dice. So you get to guess one number out of the 6 possible numbers on the first dice. You choose one number for each dice. And then on the second roll, you still only have a 1 out of 6 chance. And on the third roll, you still only have a 1 out of 6 chance. And on the fourth roll, 1 out of 6 chance. And on the fifth roll, 1 out of 6. And on the sixth roll, 1 out of 6. So in this dice rolling lottery, each time you roll the dice, nothing changes from one roll to the next. The odds of success are the same each time. But in this lottery, this first Texas lottery, where you're basically drawing balls out of a bucket, the odds of your number being picked changes each time a ball is drawn. So this is sort of connected to the with replacement, without replacement idea that I'm sure you're familiar with. So if you were to describe the pattern, your odds don't change from one event to the next. And if you were to answer this question, what are the difference between dependent and independent events? For dependent events, as one event occurs, it influences the odds of another event occurring. But independent events, there is no influence on one event to the next. Okay. So here are some practice problems to do. A die is rolled and a coin is flipped. Are these independent events? And what is the likelihood that the dice roll is even and the coin flips heads? So, does rolling a dice and flipping a coin, do those two things influence each other? The answer is no. So what is the likelihood that the roll is even and the coin flip is head? Well, there are 3 out of 6 ways I can roll even times one out of two ways that the coin can flip heads. So that's 3 times 1. 6 times 2 is 12, and that reduces to 1/4. So the probability of this, both of these events taking place is 1/4. And notice here how we're multiplying and using the counting principle to multiply together our odds to get our total odds. Alright, so guided practice 2. A bag of assorted candy contains 16 pieces, 4 of which are Jolly Ranchers. You draw 2 candies without replacement. Are these independent events? How likely is it that both candies are Jolly Ranchers? So let's think about it. Our first candy, the odds of Jolly Rancher is 4 out of 16. So if I take one candy and I don't replace it, how many candies are left the second time? And that would be only 15. So the fact that I took one candy out of the bag and didn't replace it has made these dependent events because the odds are now changing. So how likely is it that both candies are Jolly Ranchers? Well, there were 4 Jolly Ranchers over 16 out of 16, and then if I got a Jolly Rancher the first time, there would only be 3 Jolly Ranchers left. And then we multiply our odds together for 12 over whatever 15 times 16 is. Let's see, was that 240, I think. I'm going to double check that on a calculator. Yes, it is 240. And then we can reduce 12 over 240. Let's see, go shortcut way with the calculator. Oh, so it's 1/20th. Okay. So the odds on that one are 5%. So again, we have a candy problem, the same problem, but this time we're drawing 2 candies with replacement. And this time they are independent events, because we have 4 candies out of 16. How likely is it that both candies are Jolly Ranchers? 4 out of 16, so if I pick one, regardless of what it is, and I put it right back, there's still 16 candies, and there's still 4 Jolly Ranchers. So that would just be 4 out of 16, which would be 16 out of 16 times 16, but one of those is going to cancel, so that is actually 1/16. And you might want to check that on a calculator to verify for yourself. Another way to think of this is 4/16 reduces to 1/4. 1 times 1 is 1, 4 times 4 is 16. Okay. So at the end of the 1930s, roughly 12% of Americans owned a car. It's true, I looked it up. Also, in the 1930s, roughly 2% of people were allergic to dairy. That is also true. Are these independent events? And what was the probability of someone with a dairy allergy owning a car in the 1930s? So, there's no reason to think that owning a car and having a dairy allergy influence each other. So these are probably independent events. And what is the probability that a person had both of those things? Well, we would do 12% times 2%. And the likelihood that someone had both a dairy allergy and owned a car was pretty small. Only 0.0024, or let's see. Yes, that is right. 0.0024 or 0.24%. Not 24%, 0.24%. So less than 1% odds in that situation. Okay. And then here are your practice problems. And these are to be completed on Kia.